Welcome everyone. My name is Sylvain Lézé from the Department of Aeronautics at Imperial College London, and this is the new episode of the podcast Turbulence at the Exascale. So for those who are not familiar with the podcast, its aim is to gather the view of the community regarding exascale computing for turbulence research in the UK, and especially try to understand what are the challenges and opportunity about exascale computing for turbulence research. This podcast is part of the Excalibur Initiative, which is led by the Met Office, by UKRI, and its aim is to prepare the UK community for the transition to exascale computing. And I'm very happy because today our guest is Professor Simon McIntosh-Smith from Bristol. He's a professor of high performance computing. He's also heavily involved in the Excalibur Initiative. He's also the lead of the Izambar Tier 2 system, which is currently being upgraded. And more broadly, Simon is working very hard to make sure that the community, the scientific community, is ready to use the next generation of hardware systems. So good morning, Simon.
Hello, Sylvain. Thank you for having me.
My pleasure. So I'm going to start my series of questions. And for those who do not know you very well, can you tell us a bit more about yourself, where you're from, what you have studied, and where, and how did you end up professor of high performance computing in Bristol?
Sure. Well, so I'm a computer scientist. I've been at Bristol University since 2009, so nearly 12 years now. Before that, I was actually in industry. So I graduated in computer science in the early 90s. And then I went into industry as a chip designer, so as a microprocessor architect. And I was designing very high performance embedded CPUs. And actually from there went to work for a graphics company. I was designing graphics processors. This was in the late 90s, before they were used at all in high performance computing. And that's what really got me into high performance parallel processing, because graphics chips are highly parallel. I then was one of the founders of a startup called ClearSpeed, and there they were the first modern high performance computing accelerators. And they were used by Tokyo Tech to build Tsubame 1 in 2006. Tsubame 1 got into the top 10 of the top 500 supercomputers in the world using ClearSpeed accelerators. And all of these companies that I've been working for were in Bristol. So that's what brought me to the Bristol region in the mid 1990s. And I've been here ever since. And after ClearSpeed, I was looking to have a bit of a change, do something a little bit different after a few startups. And this opportunity came up at the university to do computer architecture and high performance computing in academia. And I thought, what a great opportunity. And I've been thoroughly enjoying it ever since. And having worked as one of the vendors and one of the designers, it's great to be now on the research side of the high performance computing space.
Great. And so you have been a professor in Bristol for quite some time now, and I was wondering what's the best thing about your job and about working at the University of Bristol? I mean, you said you spend a lot of time in industry, so how does it compare being an academic versus being in industry?
What's great on the academic side? Well, there's lots of different things. One of them is effectively you're an independent person once you're an academic. So when I moved into academia, I was being called on all of a sudden by things like the research councils to help out with some of the big procurements. It's useful to have somebody who was on the other side of the table in procurements now on your side, because it helps you understand how the vendors think and what really matters to them and so on. But the really great thing about being an academic is all the people you get to work with. And Bristol's got lots of really fantastic academics, get really good students. So I've got a really great team of really bright people who do really fun stuff. And Bristol itself does lots of really cool high performance computing. So we get to work in lots of multidisciplinary projects there. And from there, of course, I can work with lots of interesting industrial partners. So we've had really interesting collaborations going on with ARM. That's what will lead us into talking about Izambar soon. But previously, we've done lots of really cool stuff with Intel, with Cray, now HPE, with NVIDIA, and so on. And And in some ways, you're much freer to do those collaborations once you're an academic than you were when you were one of the industrial partners, because in many ways, everyone else is your competition then. Whereas now I'm collaborating with all of these different companies, which is really, really cool.
So you are not going to go back to industry anytime soon?
No, I can see myself carrying on doing what I'm doing until I retire. It's really great fun. I get to work with everyone in industry I want to work with and with all of the academics. So it's kind of the best of both worlds, being in this position.
Great, thank you. And before I ask you my question more specifically to your role and to Izambar in particular, a few days ago, Archer stopped in the UK, and I know you have been involved in the procurement of Archer. So can you say a few words about the legacy of Archer, I will say, and about the new Archer 2 that is currently being put in place?
Yeah, sure. Yeah, so I was involved in the procurement of Archer 1 way back when. I think we started that process in 2010, 2011. It actually went in 2013.
Yes.
And it's run even longer than we expected. And it's been a fantastic machine. One of the first things we did when starting Archer 2 was we went and spoke to all of the user community and got feedback on what's been really good about Archer, what would you like to see improved. And the feedback was just so positive. It's been a really robust service. It's been highly available. People have just been able to get on and use it and do their science, and that's been fantastic. It's been a real workhorse. So that's what we wanted to preserve for Archer 2, was for it to be a system that everyone could just get on and use, and it just do what they need from day one, and nothing complicated. It's just a big, powerful, easy to use workhorse that people can get on and do their science. So Archer 2 is a really massive step forwards. The level of increase in performance is more than we'd hoped. So it's really fantastic when it comes fully online. It's arrived at quite an interesting sort of conjunction of different technologies arriving. There's all sorts of new processors, there's all sorts of new interconnects, there's all sorts of new software stacks. So there've been a few technical hitches this time round, which we didn't have last time. But there are lights at the end of the tunnel for those now, and we think very quickly now this year, Archer 2 will come up, and it's already, even though only part of it's there, it's already faster than Archer 1 was, and when the rest of the system is there, it's going to be a monster of a machine. So hopefully that's going to serve all of the scientists who use it in the UK really well for the next 5, 6, 7 years, just like Archer 1 did.
Definitely, it's going to be amazing to use Archer 2. I can tell already. So in Bristol, you have a tier 2 system called Izambar. So and I know that Izambar is currently being updated. So can you tell us more about Izambar, and in particular, can you tell us more about your choice of hardware for Izambar?
Sure. So with tier 2 in the UK, one of the really important goals was we wanted to make sure we had good coverage across all of the different potential computer architectures for the UK. And that's because we're in a period of much greater uncertainty about what the future holds than we have been for 10 or 20 years in high performance computing. So rather than plow on as we always have, or just bet on one particular possible outcome, there was a very deliberate strategy in the UK. Let's cover all the bases. In tier 2, let's try and have one of everything so that our scientists can be used to trying all the different architectures. And then whichever one wins in the future, we'll have already gained some experience. So we shouldn't be taken by surprise by whatever happens. So that was a very deliberate choice by UKRI and EPSRC, and I think that was a very good one. So for Izambar, in the southwest of the UK, we've got the Great Western Four Alliance universities. So that's Bristol, Bath, Exeter and Cardiff, all in the southwest. And we got together and I'd previously been involved in a European project called Mont Blanc, which is led by the Barcelona Supercomputing Centre. And that was building prototypes of new supercomputers based on mobile phone chips, taking Samsung Exynos chips that were from tablets and things like that, and building a prototype system to see if you can make that work. There was lots of work to port Linux and things like that to make that happen. And it looked quite promising. The performance was poor, but the functionality was good. And what we believed was the trajectory of ARM over time was it would be a very disruptive technology because it's coming from the massive mobile space that has hundreds of billions of dollars of revenue, and eventually it would be able to benefit high performance computing. So that was sort of 2013, 2014. And then in 2016, when the tier 2 systems were being upgraded, as GW4, we put in a proposal to build a real production ARM-based supercomputer. And the timing was good because we were getting the first generation of performance competitive ARM-based server chips. There was a company called Cavium, which got bought by Marvell, which was making these chips. And so in late 2017, we got our first nodes and produced our first results, and the main system actually got installed in 2018. And it's worked fantastically well. We were getting performance results similar to the best state of the art at the time. So it's competitive with the best Intel processor at the same time, while the cost competitiveness was excellent. So the CPUs that we were buying were about a third of the cost of the equivalents from others. So that was really, really promising. And the system's been really stable. Izambar's been really easy to use. It's a Cray XC50. So if you used Archer, you could pretty much log into Izambar, recompile your software, and it generally all just worked and worked well. And you couldn't really tell it was ARM, which was what we were hoping for. So that was really promising. And then we've just upgraded the system at the end of 2020 to Izambar 2. So we were lucky to get another round of funding. So the system was really full and really busy. So we've doubled the size of the existing machine. But some really exciting new ARM-based processors have come out in the meantime as well. And that's the Fujitsu A64FX CPUs. These are the ones that Recon has used to build Fugaku, which is now the fastest supercomputer in the world as of 2020. So we have a small system of those added into Izambar as part of Izambar 2. And we're just finishing fully joining all those up. It's mainly configuring the software. And hopefully within the next few weeks, we'll make those available to all the rest of the Izambar users. We're up to about 500 registered users on Izambar now. And they'll have access to this A64FX as well as our main ThunderX2 ARM system. And also to help people do some rigorous scientific comparisons between the different architectures. We've got a little bit of everything else. And in fact, Izambar is one of the most diverse supercomputers anywhere in the world. So it's got several different generations of Intel processors, and we're about to add some Ice Lake CPUs this year. We've got different AMD processors as well. So we have some AMD Rome. We're going to add some AMD Milan later this year. And we've got several different GPUs. So we've got some NVIDIA P100s and now V100s. We'll add a few A100s and some AMD MI100s this year too. So it's a little bit of everything so that in one system, you can do some benchmarking across all the potential architectures and do some really fair apples to apples comparisons. That's what Izambar's all aimed at doing.
Great. It's a fantastic supercomputer, I think. And we're very fortunate in the UK to have it. So that's good. Right. So we talk a lot about hardware now. Let's try maybe to talk about more on the software side. So I've looked at your proceeding and publication, and recently I saw one that was called Tracking Performance Portability on the Yellow Brick Road to Exascale. So can you tell us more about this work, please?
Yeah, sure. So this diversity of different approaches is a real benefit in some ways because it means there's competition, which means that we're going to get more and better and more exciting and faster hardware at better price points than we would have done if that competition didn't exist. So that's a really positive thing. The challenge it creates for us is our software has to be able to work on all of that different hardware. And in the past, really, it's just been x86 CPUs and maybe NVIDIA GPUs, and that was really your only two choices. Now it could be CPUs from Intel or AMD or IBM or one of several different ARM vendors. It could be GPUs from NVIDIA or AMD or Intel. So there's a lot more diversity now than there was before, and the way all those things could be linked up is a real challenge. So now we need to care about not just portability of our software, does it work at all, but if I run on this supercomputer or that supercomputer, will I get good performance? And that's what we call performance portability. And performance portability doesn't just happen. If you just take your software and you recompile it and it works, that's pretty good. But it's likely that if you're highly optimized on one system, you might actually perform quite poorly on a different system. So this has become a whole big area of research in high performance computing, performance portability. The US has actually invested quite a lot in this space, and they've been running some fairly big seminars and workshops over multiple years now. There's some really great workshops at Supercomputing, for example, focused specifically on performance portability. And there's been some really nice advance in the science, and there are now some quite rigorous metrics for actually measuring performance portability in an objective way. And that means you can actually, as you work on your codes, you can measure how performance portable they are. You can find out if you're doing well or not, and you can measure the impact on performance portability as you make changes. So as you develop your code, you could put some optimizations in, and then you could measure what's that done to the performance portability metric. Has it got better or worse? And no, whereas in the past that would have been totally treated as an afterthought or completely ad hoc or guesswork. And now it's something you can actually treat quite rigorously. You could measure it. You could even class a regression in performance portability as a regression, a functional regression, and say that's not good enough. So we're now in the position where the science community can know whether as it's developing its codes, are they going to work well on all of the different kinds of hardware we might want to run on. And this isn't a hypothetical question anymore, because if you look at the next generation of supercomputers, the exascale machines that have been announced, they do cover that full range of all the different hardware. And we've got Fugaku-like machines, which are just CPUs, no GPUs at all, just CPUs. Then we've got lots of different machines in the US that all have different combinations of different CPUs with different GPUs across all the different vendors. And if you want to be able to take your code and run it on any of those, or you want to support users of your codes on any of those, you're going to have to care about performance portability. So this is a really important area now, and it's an exciting area that's seen a lot of advances. And the good news is that it is possible to write performance portable code, and we're seeing lots of examples now that are very performance portable and running fast on a wide range of different hardware.
Great. So as a follow-up question, how do you achieve portability? I mean, so let's say we are doing turbulent flow, so we have a set of equations, the Navier-Stokes equations. Now, if I were to start from scratch and if I were to write a tool so that I can use this wide range of hardware, what do you think would be the best strategy at this point in time?
That's a great question. There's no simple one answer, but there are a couple of common techniques which do really help. So one of the common approaches that people are now taking is to build things called domain-specific languages. And this is to include an extra level of abstraction so that underneath or inside your domain-specific language, you can then generate the code for whichever hardware it is you want to target. There are a couple of good examples of this within the UK. OP2 is a really good library, and O+, which for structured grids and unstructured grids let you generate code in the back end that could target different CPUs or different GPUs. And it, on your behalf, would use things like OpenMP or CUDA or Sickle or different parallel programming languages, which you as the implementer of the code then don't need to worry about. So if you like, they sort of take care of most of the performance portability for you. So that's one approach that I see being used increasingly widely, this sort of domain-specific language. Seeing some weather and climate codes. So the Met Office is writing this thing called ELFRIC to replace all their previous codes, which takes this approach. And things like OpenSBLI have a DSL as well, which do this sort of things for you. So it's becoming quite common, but not everything can work that way. If you can't do something like that, then one of the most important things is to use open standard parallel programming languages, because they maximize your chance of being portable, right? So if you use a vendor specific language, you're actually stuck even at the very beginning, right? So if you write something that will only run on one kind of GPU from a certain vendor, then that's not going to run on GPUs from a different vendor or on different CPUs. So whereas if you pick something like OpenMP or Sickle or one of these emerging widely adopted standards that's supported by many vendors, then you actually maximize your chance of writing portable code and then becoming performance portable. Performance portability is often a second step. Once you're portable, so once your code will run on these different things, how do you make it run fast? And the main advice there is to actually develop for different platforms as you develop the code. If you, the common approach is a bit of a pitfall. You tend to optimize for one specific platform. Maybe you have a main system that you tend to use, and it's got a certain kind of CPU and a certain kind of GPU, and you optimize for that. What we found from our research is that tends to lead you to over-optimize for that one platform, and it often starts to hurt performance everywhere else. Whereas if you optimize for, let's say, a CPU-only platform and a CPU plus GPU, and maybe use 2 different GPUs from 2 different vendors, then as you do an optimization, you check it on all of them, and if it helps most of them, you keep it, and if it helps a few and hurts most, then you reject that optimization. That leads to better overall performance portability. So those are the main bits of advice really. Is abstractions like domain-specific languages can really help. Using open parallel programming standards like OpenMP or Sickle or OpenCL, they really help. And then as you develop, actually develop in a performance portable fashion, targeting different hardware, preferably quite diverse hardware, so that as you add optimizations, you can check, are they actually helping across the board and not just helping one platform and hurting all of the others. And then we've got these new tools now, which actually you can rigorously measure performance portability. So you can see, have I just made things better or not?
Great, thank you very much. You mentioned a few times Sickle, and well, in the turbulence community, Sickle is not yet very well known, or not as. So can you tell us more about Sickle and maybe the specificity of this emerging language?
Sure. Well, you're right in saying the Sickle is still emerging, so it's still quite a new parallel programming language. There's been a lot of interest in the last 5 years for writing parallel programs in C++, and I think C++ is clearly quite a strong trend going in that direction, and more people developing codes that way. And if you look at the big US DOE, DoD labs, they're generally trying to make sure that all new codes are written in C++. So ways of writing parallel C++ programs have been increasingly important for the last few years. And we've seen things like Cocos emerge from Sandia, which is their own approach to writing parallel C++. There's something called Raja from Lawrence Livermore. But those were sort of, because those are projects coming out of specific sites, they are a little bit more risky to adopt for the rest of the world, because what happens to those things long term. So what you'd really like is something like a Cocos or Raja, but there was a widely supported open standard managed in some nicely sort of transparent way. And that's where Sickle comes in. So Sickle started quite a few years ago now, 2013, something like that. And originally it came out of OpenCL. So it comes from the same standards group, Kronos, that manages OpenCL and OpenGL and things like that. Initially it was targeting sort of high performance computing, but really it's the last couple of years when it's really started to take off. And partly that's because the vendors have started to get behind Sickle quite strongly in the last few years. And in fact, I think it was Intel announcing that Sickle is the core of their DP C++ approach. They needed a parallel C++, which was a standard and which they could make work on CPUs or GPUs or FPGAs. And Sickle was really the only game in town. So Intel's really got behind it. And I think that's really turbo boosted Sickle from being an interesting curiosity to it's now a serious player. And the nice thing is there are already several quite mature implementations that are available. So Intel now has their own as part of their one API approach. There's a DP C++ compiler. It's basically Sickle 2020, the latest version of the standard. That's nicely supported by the LLVM compiler, which is open source. So there's really good support there. There's another implementation from a company called CodePlay, which is actually based in Edinburgh, and they were one of the first companies to do this, so they had the very first Sickle implementation. And there's another sort of academic project, which is a really nice Sickle implementation called HipSickle, which is from a chap called Axel Alpay in Heidelberg. And that's also a really, really nice implementation. And there's a few experimental ones as well. So it feels like Sickle's time is sort of arriving. It's got good vendor backing. There are multiple choices of implementation, including some open source ones. And it provides you a really nice parallel C++ environment coming from a transparent open standard that anyone can get involved in producing that standard. So that can give you confidence about its long-term viability. So I think we'll see more and more Sickle. It's quite a nice target for backends. So your domain-specific language could generate Sickle, for example, or your library could be written in Sickle, and it takes care of a lot of the heavy lifting for you. So yeah, Sickle's one to watch, I think.
Great, thank you very much. So this podcast is part of the Excalibur Initiative, which is in the UK. The project that is going to lead the transition to exascale, and I know you are heavily involved in the Excalibur project. So can you tell us more about your role in this big project?
Sure. Well, Excalibur's super exciting because it's really, this is how we're going to get the UK's science space ready for exascale computing. We're really on the vanguard. So it's mostly focused on software and algorithms. It's not really hardware. So I'm lucky enough to be on the steering committee for the whole project. So it's a £46 million project over 5 years. So it's quite a big project for the UK. And but specifically, my main focus is on a subset of Excalibur called the hardware and enabling software project. So within Excalibur, we recognized that the exascale machines we want to target don't exist yet. So what do we do about that? We thought it really important to include an element of the project where we were very forward-looking in terms of what hardware we might have. So about 10% of the overall budget has been put into hardware and enabling software, and we put out calls every year. We're into the second round at the moment to build exciting prototypes of things that are probably only small prototypes, but things that are pre-production. And then it could be processors, but it could be storage, it could be networking, it could be middleware, anything that we think might play an important role in exascale in the future in the UK, that we think it's important to expose our software developers to, so that they can take things into account in the rest of Excalibur when they're developing new algorithms and new software. So that's what hardware enabling software is all about. So far, we've done things like build some new systems with AMD GPUs. We've got new kinds of high performance storage at Cambridge. We're getting some new hardware from there's a different kind of hardware that's optimized for artificial intelligence and machine learning. So GraphCore, which is actually a UK company, it's building processors that should do that really fast, even faster than GPUs. We're hoping to get some of that this year. There's some other hardware in a similar sort of space that we're hoping to bring into the UK that we haven't made public yet, and so on. So there's all sorts of fun stuff. We're hoping to get a small FPGA system and things like that. So that's the hardware enabling software part of Excalibur. And overall, so far, we're only sort of a year or so into Excalibur, and lots of projects are being started up, and most of it's really thinking about if we're going to a scale of computing that's 3 orders of magnitude more than we've been used to, we've really got to do some fundamental rethinking of how we do stuff. We might need completely new algorithms for solving things to exploit 3 orders of magnitude more performance, which largely comes from more parallelism. So we probably need codes that parallelize much better than they've had to in the past. Archer 1, 118,000 cores, Archer 2, 750,000 cores, and Archer 2 is only a 20, 30 petaflop machine, not 1,000 petaflop machine. So, an exascale machine will make Archer 2, all of Archer 2 look like a tiny toy by comparison. So, yeah, we've got to do some really serious thinking to get ourselves ready for exascale in the UK.
Great. this is partially answering my next question. I wanted to ask you about the readiness of the UK community and the readiness of the UK solvers for the transition to exascale computing. And do you know if some communities are more prepared than others? And yeah, I'd like to have your view on this.
Sure. So I don't think, I think it's too much to ask anyone to be ready without doing anything. I mean, how could it be? Exascale is such a big step beyond where we've been so far. It would almost be a fluke if anybody could just be ready for it without doing anything. So there's definitely work for us to do. That's what we would expect. And if you look around the world and look at the bigger economies of the world that are doing this ahead of us, so especially in the US and Japan, I would look, they've had huge programs to get their software base ready for exascale over multiple years. So the approach we're taking is exactly what you would expect. Of course, some communities might be slightly further ahead than others, and possibly the ones that are quite close to the US and Japan, and so have been part of their exascale programs already. They may be further ahead, and that's quite natural. You'd kind of expect that. But probably for most of the users in the UK, even just scaling up ready for Archer 2 is going to be a fairly big activity, and then scaling from Archer 2 onwards to what you might call pre-exascale machines that are hundreds of petaflops, and then to an exascale machine. There's still probably quite a lot of work to do, some of which could be quite fundamental. It could be fairly fundamental algorithm work, not even just optimizing code, but this algorithm's never going to scale to that size, so we need a new algorithm and then do a highly optimized version of that. So I think if anyone is already ready in the UK, that would be amazing, but we're expecting most people to be on a journey to get ready for exascale, a multi-year journey, and that's what it's taken, as we've seen with others around the world.
Great. So I'm going to ask you a slightly controversial question about this. So in Europe, there is the Euro HPC initiative, which is, I will say, very similar to the Excalibur Initiative. And do you think there's a chance for the UK to join Euro HPC, or you think that the UK is going to focus on the Excalibur Initiative?
That's a really good question. So I think things have just been coming out in the wash, haven't they, in the last few weeks? And I think we are involved in some parts of what's going on in Europe, but I think not yet Euro HPC. And I've not been involved in those discussions, so I honestly can't really give much of an opinion. I think some of what's happening in Euro HPC is really quite interesting. I think I really understand the desire to have sort of security in supply of European technology, especially given some of the trade wars that were happening in the last few years. Maybe things will settle down a little bit in the next few years, who knows, but I can understand that. So I think it's something the UK should definitely keep its eye on, and it's something we might want to be more involved with in the future if we can. But at least it sounds like we're a little bit involved in some of what's going on in Europe, and I think it's important that we find the best ways to collaborate that we can, whether our government decides we can be in the funded parts of the program or not. It would be crazy to ignore the good things that are going on and not be able to take advantage of those and contribute to those. So yes, I can't be much more specific because I haven't really been directly involved in it, but there's definitely some interesting stuff going on that we should be involved with if we can.
Great, thank you. I have a couple more questions. One is about the Azimoth project. It's more related to the turbulence community. So can you tell us more about your involvement in this big Azimoth project?
Yes, well, so Azimoth is an EPSRC prosperity partnership. So these are special kinds of projects which are usually industrially led, and they bring together a company with a really interesting challenge and universities who want to help solve those problems. So Azimoth is a Rolls-Royce led project, and it involves Bristol University along with Edinburgh, who's the academic lead, and Cambridge, Oxford and Warwick, and a couple of small companies as well in this space like Xenotech. And we're 2 years into a 5-year program. And ultimately, what we're trying to do is get Rolls-Royce into the exascale era, and that's what it's all about. And for them, they'd really like to be able to design future gas turbines entirely in simulation, right? And today that's totally impossible. It's that science fiction, but small parts of it are feasible. And as part of Azimoth, we've been working on new solvers, new codes, and even new computer architectures. My part of that project is actually looking at what would ideal processors look like to solve these sorts of problems. And it's all been very interesting so far. We're trying, Rolls-Royce, even just 2 years in, is already now doing some simulations much bigger than anything they've ever done before. And we've got some goals that by the end of the 5 years, they've got some very specific things they want to be able to achieve. There'll be a massive step forwards. They won't be able to do a full, virtual jet engine design in 5 years, but some of the fundamental problems will have been solved, and there should be a good roadmap to actually achieving their end goal, which might take another 5 years after that. But that's where it's headed. That's where they want to get to.
Good, thank you. And I have one final question. We are talking a lot about the transition to exascale, but I guess we need to think about what will come next. And I wanted to have your view about where high performance computing is heading in the future. Are we just going to stick to CPU and GPUs and evolution of those technology, or are we going to have some crazy new hardware coming in the next 10, 15, 20 years? What's your view on that?
That's such a good question, isn't it? And of course, no one knows, but we've all got opinions. So I can share my opinion, but I might be totally wrong. So one of the things I like doing is looking at what the fundamental trends are. And there are some really very basic fundamental trends which can inform your guesswork about what might happen in the future. So for example, Moore's law. So Moore's law hasn't ended yet, but it is slowing down. We're now doubling transistor density every 3 years instead of every 2. That's likely to carry on for a while. TSMC, which is the biggest manufacturing facility in the world, which develops all the Apple chips, for example, in iPhones, all go through TSMC. They're on 5 nanometer, which is currently the leading manufacturing process. They've got roadmaps of 3 nanometer and 2 nanometer. So probably still for the next 10 years or so, we'll keep going down similar routes to what we're doing right now. And with more transistors, we can put more cores on a chip. Cores can have wider vectors. We can have more memory on a chip. And we can also stick more and more chips together inside one package. And this whole kind of chiplet approach is a new thing, which we started to see AMD's using that. So AMD Rome, it's actually 8 chiplets of 8 cores to make a 64-core CPU. And I think all the main vendors will go down that route. So in some ways, that's just more of what we've been doing. So I think we'll see for the next 5 or 10 years, it's still mostly more CPUs, more GPUs, more high bandwidth memory, possibly more integrated networks, because networks could be a chiplet, which might give some real benefits in terms of latencies and things like that. Then I think beyond that, we are actually then going to be towards the end of Moore's law. So we're already at the point where one transistor is of the order of 100 atoms or so. So we can't make them an awful lot more smaller. So what do we do next? And no one's very sure, but there are a whole swathe of different avenues people are exploring, from optical computing, using photons stuff to compute things, to carbon nanotubes and memristors and all sorts of exotic things, which initially will probably augment silicon and then eventually might replace silicon even further out. But initially we'll probably have silicon plus different things, possibly with more and more accelerators. So today we think of an accelerator like a GPU, but we're now seeing things like tensor cores starting to appear in more and more processors. So that's a new kind of accelerator, sort of a mini vector matrix accelerator inside the processor. And what's to stop us having accelerators for encryption or compression or all kinds of other things that we do in silicon? If we can't just use it for more and more cores, maybe we can have more and more sort of standard accelerators. So I think we will see increased heterogeneity in the future. Hopefully those things will be wrapped up under software. So it'll just be as you use a library, it will use those bits of hardware. You don't have to program for many, many different things yourself. That will be a bit too much of a burden, I think, for most developers. So we need more sort of standard libraries that we can exploit, which under the hood can use these bits of hardware. But I think that's the likely sort of medium term is increased heterogeneity, more libraries and hardware acceleration for more functions. FPGAs, I'm still not sure. I've been saying that about FPGAs for the last 20 years. It feels like for very specific areas, they can have a real benefit, but they're so hard to use for most developers. And they could either give you no benefit or lots of benefit. So they're quite peaky in exactly what they help for. So that's, again, worth keeping an eye on. But I'm not expecting them to kind of come in and take over HPC anytime soon. It would take some quite radical breakthroughs in ease of use and efficiency, I think, for that to happen. So more evolutionary, I think, than revolutionary, at least for the next 5 or 10 years. And then we're going to start hitting the wall. So we'll need a bit more revolution then, I think.
Great. Thank you very much, Simon, for your time and for your input. It was very nice talking to you, and we wish you all the best for your future endeavors, and best of luck for Izambar 2, who with this new set of hardware. So thank you very much. That's it for today. If you want to learn more about the UK Turbulence Consortium or about the Excalibur Initiative, you can go on the UK Turbulence website, or you can follow us on Twitter, UK Turbulence in one word. The recording of the podcast are available on the website, and I will put some links on Twitter as well. So thank you very much, everyone, and hope to see you soon for a new episode.